Welcome back, everyone. We're going to continue our video on maximizing polynomials. The last video was on two-dimensional objects, specifically a rectangular pen. And today we're going to look at, or this video, we're going to look at maximizing a three-dimensional object. So that would be volume instead of area. So you see here I have volume underlined because we're now talking three dimensions. We're going to give ourselves a nice little diagram to go with this. We're talking about cutting squares from the corner of a rectangular piece of sheet metal. So let's get this rectangular piece of sheet metal here. There it is. And we're going to cut squares out of the corners. So we'll cut some squares out of the corners here as well. Now the idea, and I know it doesn't say that there, but the idea here is that each corner square is going to be the same size. Alright, so we're going to label each of those an unknown length. They're all going to be x by x squares. Now we're told this piece of sheet metal has dimensions 10 inches by 15 inches. So based on perception here, we'll call this one the 10 and this guy here the 15. Alright, so there are our dimensions. Now what happens when I cut these corners out, it's kind of neat. We're going to end up with kind of like a plus sign, if you will, right? Cut the corner out. And our rectangle becomes this funky plus sign. Okay, now remember we cut out x by x here, and this length was 10. Well, what's this dimension going to be now? Well, it's 10 minus the 2 x's I cut from it. And likewise, this will be 15 minus the 2 x's I cut from it. And remember, these guys were x and x. So how do you make this into a box now? Well, we're going to take this portion here and fold it up. We're going to take this portion right here and fold it up. Right? We're going to bend it right up. Same deal over here. And same deal here. So those things are all going to pop up. It'll be like a little box you got there. All right, so volume of a box. Length times width times height. Let's see what our box looks like here, and then we can come up with our equation pretty easily. So I'm folding up the sides. So that flat piece of sheet metal will now become a box. The height is x. This dimension we said was 10 minus 2x, and this one is 15 minus 2x. So length times width times height, all right in front of us there, easy peasy. Now the beauty of it, writing it like this, is we know so much about graphing polynomials. I can now graph this guy, and we have the zeros right in front of us there. So, plotting my zeros here, we're going to get a 0 at 0. 7.5 and 5. 0, 5, and 7.5. This is our x value, which remember x is our height, our cutout. And this is v of x, our volume. We know this is a positive cubic. Two negatives, right? Negative 2x and negative 2x, and a positive x. That's a positive cubic. So I'm going to go through my zeros in a linear manner since they came from linear roots. And my goal here, remember, is to maximize. So I'm looking for this value right there. If it was quadratic, no problem. Oh, 2.5 is the middle because quadratics are symmetrical. However, this is cubic. It is not symmetrical. Okay, so we cannot say 2.5 is the right value. However, 2.5 is going to play into this here at some point. So let's go to our calculator now. We're going to enter that equation in here. The window. Notice my x values are from 0 to 5. Why would that be? We know the maximum's in here, and that's between 0 and 5. I know it's not over here. Right? You can't have negative area, or volume in this case. Negative volume. That has no real-world meaning. So our realistic domain is when x is between 0 and 5. Right? It can't be 0 or else you'd have no height, and it can't be 5 because if it was 5, you have no length or width, whatever you would like to call that one there. Okay, so realistically, our values have to be between 0 and 5. We see that on the graph, and we see that from the equation. So, 0 to 5. Now, how did I get 200 for my y max? Well, again, I told you this 2.5 would play in. We know 2.5 is close to the x value. That's the answer. So if you want to do 2.5, that's fine. If you want to use 2 or 3, that's fine too. The bottom line is you need to know their approximations. So if I want to find v of 2.5, because I want to know an approximate volume, remember what that means. X is 2.5. How did we turn blue there after all that? X is 2.5. So 15 minus 5 and 10 minus 5. So that gives us 125 as an approximate volume. I might be low, I might be high, I don't know. Okay? So I'm going to go up to 200 instead of 125. 150 would probably work, but why not be on the safe side? We'll now graph it. There's our graph. 200 is plenty high. The volume that maximizes is right here. How do we find that? Second trace. Maximum is number 4. It's asking for a left bound, so we know the max is in here. So I'm going to go to the left of it and hit enter. Now it wants a right bound, so I'll go to the right of the top. Hit enter, and the guess, well, let's take a guess somewhere in between. Enter. And there's our answer. We'll drag that onto here. And the maximum x value, the x value that maximizes the volume. Okay, so V of 1.96 is approximately equal to 132 cubic inches. Couple different questions can come out of this. I can ask you for maximum volume, 132 cubic inches. I could ask you for the size of the cutout that maximizes volume, 1.96 inches. I could ask you for the dimensions of a box that maximizes the volume, in which case you have 1.96 and then 15 minus what? Almost 4, so 11, and 10 minus almost 4, so 6. You'd say like 2 by 11 by 6. Okay, so a lot of different questions come from this problem. Make sure you're reading the question and know what you're answering. That is the video on maximizing the volume of a box from a rectangular piece of sheet metal. Stay tuned for further shapes. Have a good one.